All right, well, welcome to webinar number 2. My name is Jake Beers, Elementary Science TOSA with Springdale Public Schools.
And I'm Jenny Gamble. I'm the K-5 STEM Specialist for the Northwest Arkansas Co-op.
And so we're excited today to talk about the science and engineering practices of NGSS and really jump in as we go. So we were having some issues with our Zoom webinar, so this is just going to be a non-audience feedback PD today. I'm going to jump over that webinar box. So this is the second of 6 webinar series in this webinar series we're doing. So the first one was about unpacking the 3 dimensions of NGSS. And this one, again, is Tuesday, January 23rd. We're doing science and engineering practices. And then the next one will be Monday, February 19th during the school day. And we're going to do that as part of our professional development day. And then we're going to do the engineering design process on that day. And again, you can check out any of the previous versions that are recorded, as well as this recorded version on our district PD site. So the agenda today really is just to run through the science and engineering practices. We're going to look at how they integrate into the new science standards and how they're an integral part of your classroom instruction. We're going to look at a classroom video from the teaching channel and then look at application. How can we apply the science and engineering practices? So as we looked at last time, the next generation science standards and the Arkansas K-12 science standards are identical at the K-5 level. And so you'll hear those kind of interchangeable terms, NGSS and Arkansas K-12 science standards. You'll even notice the colors are the same. So they're, for all intents and purposes, we're going to call them the NGSS, and we may even call them the Arkansas K-12. It depends on the moment. But they're the same. And if you look at either curriculum document, you're able to identify similar standards.
And Jake, I just want to clarify that if you've heard them called the Common Core Science Standards, those do not exist. So if you hear that, we don't know what those are. They're not in existence.
All right. So when we look at the NGSS, we have these 3 dimensions. So we have the practices, which we're going to talk in more in depth today. We also have the cross-cutting concepts, which are just these big frameworks for science, and then the disciplinary core ideas. So previous science standards would mostly focus on the core ideas, the content of the standards, and today we're going to begin to flesh out more how the practices help students to engage in the process of science. So there are 8 practices. We looked at them last week. We're going to come back to those later. Asking questions, developing models, planning and carrying out investigations, analyzing data using mathematics and computational thinking, constructing explanations, engaging in arguments from evidence, and obtaining, evaluating, and communicating information. So again, that's what we're going to focus on today. Our cross-cutting concepts, we're going to jump over those today, but remember, those are the big overarching themes of science, things that can be interwoven into multiple disciplines. We see patterns in forces of motion. We also see patterns in life science. And so we can make the connections across the science disciplines. And they're also a way for us to think of the interconnectability of the science concepts. And then again, we have our 4 disciplinary core ideas, including the addition of engineering technology and the application of science. And that's a new component to our science disciplines. So again, as we've gone through this web series, we talked a lot about how teaching science using the 3 dimensions of NGSS requires some shifts in instructional practices. And so hopefully this webinar series equips you with some simple tools in your classroom to make that instructional shift.
So before we make that shift, we want to talk for a minute about how we learn science as students and how you learn science in school. And so just want you to think about that for a minute. What was your experience like growing up in an elementary classroom, middle school, high school, even college? How did you learn science? And so as you think about that, just, what materials did you use? What did your teacher do? And how does that look different from today's, the way that we're teaching science today? And so probably what comes to mind first for me, and I know as Jake and I were talking about this, it was the scientific method. So Jake, can you bring up that slide? So everyone's probably seen this poster. You may actually have it in your classroom right now, or you saw it in a classroom that you were in as a child. But you know, the scientific method, what speaks to you about this poster? And so as Jake and I were talking through this webinar, we thought about some things with the scientific method that are still true today, but have also changed. So Jake, pull that next. So the problems that we see with this method, and that scientists honestly have been seeing with this method for years, is that the method is very rigid. It's lockstep. You follow, you find out your purpose, and then you research it, and then you propose a hypothesis, and then it's very formulaic. This is what you do every time you do an experiment. You follow this. And so, you know, what we know to be true and what scientists will say is it's not authentic to the field of science. There are components of this. In fact, every component takes place at some point in science and when you're exploring a problem, but it doesn't happen in this rote method. And so as a result, we are not teaching this method in NGSS anymore. So just, you know that. If you have this poster, you may actually want to take it down.
And again, I think the important thing is that the components are there, right? All these pieces are still part of the scientific process, but just teaching the formulaic rigid method is the big shift. Yeah.
And so as a result, we've shifted then to the science and engineering practices. And so we're going to look now at how these practices are put in place in a classroom, and how they engage students. We want you to, this purpose for viewing is, you know, how do the practices engage students in thinking deeply about science?
Sorry, my link wasn't working.
So we're going to take this video from the teaching channel.
More energy in the bounce. That's really the kinetic energy. As teachers, if we really find ways to get kids actively engaged.
Why? What's happening?
They're going to share what they've learned about science. They're going to be curious about things they see on television and that they read in the news. And hopefully then we'll have more people that really enjoy science and understand science.
As you engage in your science performance, we'll want you to be thinking about what you're doing. Specifically, we'll be talking a lot about the practices. The next generation science standards include 3 dimensions: science and engineering practices, the disciplinary core ideas, and the cross-cutting concepts. I'd like you to think about that intersection of the 3 dimensions and where it's coming together in the classroom. For those of you that are familiar with the practices, there are 8. Today we engage teachers in practices found within the framework for K-12 science education. They're designed for students. They're what we want students to be doing. The science performance that the participants engaged in today was specifically analyzing and interpreting data. We want to look at the scientific process, and that this is what scientists go through in the real world.
As teachers, it's important for us to scaffold those experiences, especially early on, to make sure that they understand how to organize their data and look for patterns and evidence. So I think as they engage in these practices more often, I think they're really going to own those practices along with the content. All we're changing is the height. It's important that kids are constructing explanations, that they are constructing arguments. Started at 70. They're using evidence and they're communicating their findings.
In groups of 3, you will investigate the height that a golf ball bounces off of a hard surface. You'll choose 4 different drop heights. After you drop it, where it returns at its peak is going to be its bounce height.
That one's a 16.
Make sure you analyze your data with your groups. And then once you've identified the patterns, you're not done. You need to talk about what's causing those patterns to occur. What's the science behind this? What's happening?
Right.
More gravitational potential energy, since all we're changing is the height. So we looked at that data to continue to look for that linear relationship. So that's a pretty traditional activity that you might do in terms of looking at the bounce height. But by really looking at the data closely and having to look for those relationships, it really increased the depth of that particular investigation.
So the lower you dropped it, the lower it bounced.
Closer it got back to its original.
So what does that tell you?
Nicole came by and we showed her our graph and our percentage difference, and she said, well, so why does that happen? What's going on? And that added really another layer of depth, because we started talking about gravitational potential energy, kinetic energy, and then we shared out and really probed that in more depth. The more kinetic energy we have, like a ratio, really made us think more deeply about gravity, energy, friction, and the system that was involved. So it was more than averaging data, calculating data, writing a conclusion. It really became more about why and what type of evidence do we have to really construct an explanation.
Any other patterns?
The higher the drop height, the larger difference between drop height and bounce height.
What's causing that pattern to occur? Yeah.
Because gravity doesn't change. The system's constant.
Is there even a more simple pattern than that? Yeah.
It always bounced less than it was stopped from.
Why? What's causing that to happen?
So all of those different ideas that are in the science and engineering practices really get kids actively engaged. So they're really thinking. It's not confirming, but looking for more information. That focus on evidence-based explanations is really key, and I think is essential in those practices.
What's different when you're having to analyze to come up with that?
Discovery. You're going to remember it more because you're doing it.
You're doing it. They're involved in doing it. That thinking process that goes on behind it is so much more critical than just receiving that information.
I'm really most excited about bringing home those ideas of thinking about labs that I already do that really could, be so much better if I really am more mindful of the science and engineering practices.
This particular performance really did emphasize analyzing data, yet a lot of you were starting to ask questions, which is exactly what we want to have happen. It's, again, an interrelated part of those practices coming out. You're using other practices at the same time.
So yeah, you're going to start at 40 centimeters. We started out gathering information, but once we started analyzing our data, we really realized we needed more data. So we went back and gathered more data. It was really a fluid process. The more we learned, the more that we did, the more questions that we had.
That works. 78.
Are you losing that each time it bounces?
Some of the excitement that I've seen with teachers is that they realize that this is really how learning occurs. Teachers that are teaching both science and mathematics can see how these practices really do interconnect.
And we had
84, so we were close. Yeah.
I think that video does a great job of talking about how the practices are interrelated. That video, they analyze and interpret data, right? But they also, like you said, ask questions. They also they carried out an investigation, right? They were dropping a golf ball, and they have to know the steps of that investigation. And then they had to use their mathematical computational thinking to begin to think about what could be causing it, right? And in that lesson, they never constructed an explanation, but when you think about taking the science knowledge, you'd eventually have to be in to construct an explanation to back up your findings. So I think that's a cool thing about the practices is that though one practice may be highlighted in a lesson, there's a great opportunity to interwove them throughout. And so when we think about where we find the practices, remember from our first webinar, if you weren't with us, every single one of our performance expectations, which is now what we call our science standards, more jargon for you, has this blue practice. And so in all of our unit plans, you'll identify that each of our practices are color-coded so that you can identify which practice. So in this one, it's using information from several sources to begin to look at develop an evidence-based claim, and then eventually compare multiple solutions is an engineering practice. So know that every time you see those blue components, they're one of the 3 dimensions and they're specific to our practice. And so how could you use these in your classroom?
Yeah, so going back to the video for a minute, we didn't touch on this before we showed the video, but something that she pointed out, Nicole pointed out, is, or that the teacher said at the very end of the lesson, was that this was very discovery oriented. And whereas science teaching in the past has been very explicit instruction, and the science and engineering practices lead kids to be discoverers, to be inquirers. So I just wanted to point that out before you think about how you could use the practices in your classroom.
Well, and that's actually a great segue. So thanks for doing that. So as we look at one of our 4th grade lessons, for example, we begin with this guitar string oscillation. So this is the first thing that kids see in this whole unit on waves, is we look at these guitar strings. We begin to make, what do I notice? What do I wonder? What do I observe? Yeah. And you may notice that's also Stairway to Heaven. So, I mean, like, you can't, you got.
They wouldn't notice that though, Jake. Kids wouldn't.
No, but when you look at those guitar strings, you wonder, what is going on?
Yeah.
Why are they vibrating? Why are they making that unique shape? And so we then, in this lesson, we launch into some jump ropes, and kids move jump ropes in different waves and different wave patterns, and begin to realize that I can create a pattern when I move a jump rope back and forth. And I begin to draw out what I've observed and look at. So begin to think about questions that I may have. Why does that happen? How can I make that repeating pattern? And then students look at another slinky, or another phenomenon by looking at a slinky and trying to create other waves with the slinky, and looking at how the waves created in a slinky are different or similar to the waves created in the jump rope. And in the end, they begin to develop a model of what a wave looks like. And so after they've explored and analyzed some data, they begin to apply these terms like amplitude and wavelength. And so instead of introducing amplitude and wavelength and having students memorize those terms, allowing them to explore, discover for themselves first, and giving them a purpose. But looking at that guitar string, it allows them to just launch into something that they're interested in, something that they would care about.
And I remember the teacher, again, when Nicole was questioning them at the end, she said, we're going to remember it more because we've discovered it for ourselves instead of having someone tell us what it is.
Yeah. And what I want you to notice too on this lesson plan is that in our Spring Note lesson plans, you'll see that all of the performance expectations are color-coded. And then underneath it, I've outlined kind of the key practices that this lesson focuses on. So notice that there's always usually more than one practice that every lesson is going to focus on, though that may be there may be one specific one in the performance expectation. You still need to incorporate multiple practices in your lessons to support your students. You also notice that I've called out the cross-cutting concepts. And in the video, they talked a lot about patterns. What pattern do you see happening over time? And so you usually will have that component of their standard as well. And so when we're going to dive deeper in Webinar 5, but we're going to look at a CER lesson there. But that's another way that this looks like, and hopefully that the lesson we just looked at gave you an idea of what these look like.
And if you're not familiar, CER, he's referring to claims, evidence, and reasoning. And that's probably biggest bang for your buck. It has so many crossovers into other content areas. So that's going to be a great webinar.
Yeah, I agree. All right, so there are a couple resources that you have access to that are open on the web. Number one is just getting your kids to see what the science and engineering practices are. So I really would utilize this blue poster on the left. There's a lot of different science and engineering practices poster, but having some way for your kids to discuss, hey, we're going to focus on these several practices today, or just calling them out as you go. Kids don't need to memorize the practices, but having an understanding of, today I'm going to be developing a model, having them understand that, I think is really important. So whether it's a classroom poster or just emphasizing it at the beginning of your end of a lesson, I think is a key component to bringing the practices into your lessons. And then this is a great graphic. I think it shows the correlation between ELA, math, and science practices. And it may look a little overwhelming, but just know that there's so much interconnectability between the practices we look at in math, science, and ELA. And then one more document I think is helpful is this is a matrix, and it shows each of the practices. So this is asking a question, and it kind of gives you, here's what the practice is at the top, and then here's the kind of what it looks like in K2, and how does that build in 3.5, how does that build in 6.8, and then how does it build all the way up to 9.12. And so showing that each of these practices are scalable to K2 all the way up through 9.12 is a critical part of our NGSS standards, and showing that starting in kindergarten, kids beginning to expose our kids to developing models, asking questions, and continuing to grow their science background and understanding as time goes on.
And I think what's powerful about this document is it shows that it does have to be built over time. You just can't start teaching science in 6th grade and expect that kids are going to be able to ask questions and define problems at the level that they should be at for a 6th grader. So, you know, as I say, science begins in kindergarten. And this document really points that out.
I'd agree. I think that's a great point. All right. So if you have any questions, you know how to reach me. And if you have any questions for Jenny, you can shoot me an email and I'll pass them on to Jenny as well. But know that we're both here to support you guys as we implement the new science and engineering practices.
Thanks so much for having me today, Jake.
All right. Well, Spring Hill teachers, if you watch this webinar, there's a link on the webinar site for a place where you can get 1 hour PD credit for doing this and completing the Google form. And again, we are excited to continue to host these webinars and continue to share how teachers can teach science.